So let's start with introductions. So today's webinar is hosted with Peter Liu from Luminary Cloud and Rishi Ranad from NVIDIA. Just a quick intro for Peter. Peter is our VP of Solutions Engineering and Customer Success here at Luminary Cloud. He's got a lot of experience in engineering simulation, high-performance computing, and cloud computing. And he's got a wealth of experience working with our customers and our innovative projects that we all work on with them. And a quick introduction for Rishi too. He's a senior technical engineer, physics-based machine learning at NVIDIA. Currently, he works in the product team at NVIDIA, where he's focused on research, development, integration of various AI ML technologies in simulation workflows, enabling and accelerating accurate modeling of engineering applications. So very relevant to what we're going to talk about today. So just a bit of housekeeping and admin. There are two buttons on the bottom of your screen which you should pay attention to. The first one is the Q&A on the right, where please feel free to add questions, anything you'd like to ask in that button. Click that button and we'll see them. We'll leave Q&A towards the end of the session to answer live. The other button on the left, resources. There's a bunch of links there and PDFs to our V&V cases, as well as some of the NVIDIA material that is going to be talked about today. Okay, right now I'm going to hand it off to Peter to get started with the webinar. Thank you, Peter.
Thank you so much, Jason. And thank you, Odin, for joining today. My name is Peter Liu. I lead our solution engineering at Luminary, and I'm very excited to, together with my co-presenter, Rishi, to share with you some of the projects that we're working on. I have been a CFD practitioner for the last 15 years. And when the wave of AI revolution come around about 2 years ago, you're probably like me. We have a lot of doubts. Is there any practical value of AI in CAE? And is the accuracy going to be good enough for what we do for aerodynamic design? So we embarked this journey at Luminary and have been working hard to answer some of those questions. And I have to say, this project has changed my belief, and hopefully you'll see some of the results that we're showing today. And we'd love to give you a behind-the-scenes look of what we have done with Physics AI in partnership with NVIDIA and Honda, and some of the results that we have got as well. Now, many of you are quite familiar with the CFD design process or vehicle design process in automotive. Generally, it starts with design studio. The designer will have a sketch, design a concept of the car, and once the concept is formulated and then translate to something like a blender to visualize it, to do the styling, and then CFD generally comes a little bit later in the design phase. So where it then later passed to the CFD engineers to understand the performance. Now, oftentimes the styles and the CFD, what CFD engineer want, can be conflict, right? So there's some negotiation going on to adjust, the taper on the back end a little bit to reduce the weight and things like that. And while design is everything, generally speaking, for automotive, people buy cars because the brand, because of design. Well, actually, if you're attending this webinar, you might be buying a car because of its aerodynamics, but it's fair to say most people buy a car because of the look, right? Because of the style. And when we work with some of our automotive partners, they come to us with a challenge. Now, is there a way we can develop a tool to provide instant CFD feedback to designers and allow them to actually understand the performance of the car early on in the design phase so they can actually incorporate CFD into the early design phase without actually having any CFD knowledge? And I'd love to show you what we get to, and we can talk about how the behind the theme. What we're able to develop is actually a physics AI model and embedded into a tool that designer use. Many designers out there use Blender or Alias. In this particular case, we have this plugin into Blender, where as a designer, I can take one of my designs and click just an inference button, and you can immediately get feedback on the performance of the vehicle, lift, downforce, and pressure, and water, and things like that. But also you can actually morph. You can use sculpting tool. You can have different ways to change the geometry. And as soon as you change the geometry, instantly you can collect inference and you can get immediate feedback on how this new design compared to what you have in the past. It provides a very powerful tool in the early design phase to the designer to be able to really kind of compare different designs, understand the performance without the need to go through the loop of CFD simulations. And obviously you can right there to look at the results right away. And when we showed this to our partners, and they're quite excited. And obviously the simple question is, what's the accuracy, right? How accurate it is. And we spent a lot of time to looking through that as well. Now, just talk about a little bit the process of developing this model. The process we follow quite similar to most of the AI ML pipeline. We start with data, high quality, high fidelity CFD data. So with those data, then we pre-process it in a format that the model can consume. And we pass that into model training. Once the model is trained, then we can pass it over to physics AI inferencing and visualization. And that's fairly lightweight, and that can be embedded into different visualization technology out there. Now, this whole journey actually started last November when we started collaborating and we're working with NVIDIA on this concept of virtual wind tunnel in Omniverse. And we actually come pretty far. We're able to put the whole framework together. We're able to generate the data, visualize the data, all inside Omniverse, and have amazing animation as you see here. But if you're a CFD practitioner like me, you probably will look closer at the data or the results, and you'll question, okay, how accurate is it? Is that actually the flow here makes sense? Now we look at this and take a look at accuracy. And what we recognize is that, well, the accuracy is not completely there yet. And what are the challenges there? We recognize data is actually the bottleneck here to create a very high quality, high fidelity physics AI model. There's lots of data out there for large language model. You can scrape the internet, you can pull a lot of data out of it, but there's actually very few public domain or open source physics related data in CAE space that you can use to training. We're not talking about just a dozen simulation. We're talking about hundreds, if not thousands and tens of thousands simulations. And that's the level of data that we need to get to the accuracy that we expect. So that's what we have been focusing on at Luminary ever since. We have developed in the past 5 years a cloud native and GPU native CFD solver. And the amazing part is that we can run simulation extremely fast. We're talking about RAN simulation in the order of 5 minutes and DDS simulation in the order of an hour or so. But not only that, we also focus on the ability to run tens and hundreds of those simulations concurrently, which is crucial to be able to generate the data set concurrently and very fast. And we support both RANs, DES, LES, and the whole range of fidelity. For this particular work that we're showing you today, we're actually using our DES solver with SA turbulence model. And as you can see, we're solving time accurate, but we're using time average solution to use to train the model. Now, with that, we also take a wider look of the whole ecosystem, and we're very fortunate to have lots of partners in this ecosystem already to support the physics AI model development process. Generally, we break this down into 4 buckets. So we start with design generation. So that is basically using CAD or STL tools and things like that to generate different designs to populate the design space. Once we have all those designs that feed into Luminary Cloud, and that's where Luminary Cloud really shines, is to able to run those designs at high fidelity or concurrently to be able to generate a data set for the training. Once the data is generated, then we feed into the model training framework. So where it's great to partner with a company like NVIDIA has developed PhysicsNeMo models, and we will go into details. But there's also other company out there like Nevasto, PhysicsX, NeuroConcept that have developed amazing technology to train the model. Now, once the model is trained, it's great. It's very lightweight, so it's very portable, and you can deploy it anywhere for inferencing. So you can use a tool that designers use, such as Blender, Alias, but also you can put it into spatial computing like Vision Pro or NVIDIA Omniverse to visualize and understand the design and the results. Now, let's put this whole framework in action, and let's see how that works out. So we started wanting to kind of select a problem that's relevant to the industry. And we decided to select Aero SUV platform for this initial data set. And I want to acknowledge FKFS for their support and providing the Aero SUV geometry to develop this data set. There are already a few open source data set out there in the market. So the DriveAir ML was developed by Neil Ashton for the CFD4 workshop. There's also the DriveAir Net++ by the MIT research group that's RANS-based. But there isn't any SUV-like geometry data set exist. And if you're tuning in from the state side, if you look at the roads, our roads is heavily populated by the SUV cars with SUVs. And that's when we talk to our OEM partners, and that's something that they're all very interested in. The Aero SUV geometry has quite a few different variations, which is great. So it gave us opportunity to create a very large data set of all the variation of the designs. It has a detailed underbody, a smooth underbody. You can have open cooling and closed cooling system and things like that. But also on top of that, we work closely with our partner at Honda to able to define some of the design changes where a designer and OEM cares about. So we have identified a number of design changes that we can make and to populate the entire design space. And those are the continuous changes. So meaning that you can stretch the vehicle continuously. So we're able to finally down for the initial data set, we down selected that we decided to go with a smooth underbody. We're going to have both estate and notchback geometries with a closed cooling system. We also decided on 7 design variables they're going to start with and to kind of morph the geometry that way. And we use Latin hypercube sampling to be able to populate as much as we can the design space with this initial data set. The result of it is that we use this morphing cage, and we're able to stretch the vortices on the morphing cage. And as you're stretching the cage, in turn, the geometry inside gets stretched. So using those methods, we're able to generate all those variation of the geometries for this initial data set. And the result of it looked like this. This is a side view of all the different geometries that we've generated. And imagine there's 2,000 of them now that we have generated. And internally at Luminary, we actually play this game that we pause the video at some point, and we can pick the closest vehicle on the market that looks like they shape. And surprisingly, this variation actually covers a quite wide range of shapes that you see what's on the road already. So with those shapes generated now, and it looks like this. And again, imagine there's thousands of those different geometries that we have now generated. And the next step is to mesh it. So in this particular work, we use ANSA to create a mesh, and we're following the best practices from Auto CFD4 workshop to make sure we have the right refinement region to capture the wake and resolve the geometry well. Now, once we have the mesh, the next step is data generation. So that got feeding to all those geometry and meshes got feeding to Luminary Cloud. And we already talked in details about our solver, but we're able to run those geometries concurrently and generate those data sets. And these are, again, high quality, high fidelity simulations. So we're talking about running DES simulations, and you can see you can actually resolve the wake quite well, which is quite critical for a SUV, which is pretty much a bluff body. So the wake structure behind the vehicle is quite critical for predicting the drag. Now, once the results, the simulation results is generated, the next step is model training. And here we partner with NVIDIA to use PhysicsNeMo framework. And there's no better person I can think of to talk about this than the author of Domino model, which is part of the PhysicsNeMo framework. So Rishi, I'll pass over to you.
Yeah, thank you, Peter, and thanks everyone for attending this webinar. So I'm going to be talking about the PhysicsNeMo, NVIDIA's PhysicsNeMo framework, and go into some more technical detail of the model architecture, and then hand it back to Peter to describe the results. So PhysicsNeMo is an enterprise-grade framework and toolkit that NVIDIA is building for developing physics AI models. The main goal of PhysicsNeMo is to enable ISVs such as Luminary Cloud, automotive engineers, simulation engineers, machine learning researchers to build these solutions, build physics solutions faster. Peter mentioned the importance of data sets and having these large data sets in the context of physics simulations. But when it comes to simulation data sets, you often run into challenges of scale, complexity, non-linearity, and so on. So to be able to take these data sets and actually build a model from it, it's a tough task. And that is the task, or that is the journey PhysicsNeMo has embarked on. So the PhysicsNeMo framework provides you all the utilities, functionalities, workflows that enable the community to take data sets and build accurate, generalizable, scalable physics AI models out of them. In the context of automotive aerodynamics, PhysicsNeMo has built-in AI pipelines. So this includes benchmarked model architectures. So model architecture specifically meant for external aerodynamics and benchmarked on some of the open source data sets that Peter mentioned earlier, such as DriverML and DriverNet. GPU accelerated data pipes. So ingesting these large scale data sets with high volume and surface mesh counts in a scalable and optimized way, and feeding them to the model architecture. So PhysicsNeMo has those data pipes in place. And of course, physics AI utility. So the ability to embed physics and physical losses and constraints into the model architecture. Apart from these pipelines, PhysicsNeMo also provides, in certain cases, especially for automotive aero, pre-trained checkpoints. So the goal of providing these pre-trained checkpoints is to provide a starting point for the community to use these checkpoints and either further fine-tune them or use them for quick design analysis. And finally, parallelized training and inference workflows. End-to-end workflows that make it easy and provide a great starting point for building some of these physics AI solutions. Next slide, please, Peter. Yeah, so in the context of automotive aerodynamics, I'm going to discuss, or CFD, I'm going to discuss some of the AI models that we have provided so these are model architectures that we provided in the PhysicsNeMo library. And so the four architectures we have are FICConvNet, XAeroNet. So FICConvNet is a point cloud-based architecture. It has a UNet plus point convolution combination. XAeroNet is the mesh graph net, but the mesh graph net scaled to handle million cell meshes. The third one is the aerograph net, which is the original mesh graph net, and finally the domino, which is the point convolution neural operator that NVIDIA recently released. On this slide, we provide certain trade-offs between these architectures, which enable the user to basically choose one or the other based on the application physics that they are trying to model. So for this work, Peter and the Luminary Cloud team, they use Domino with the PhysicsNeMo framework to train the data that was generated for this use case. So next, I'll go a bit more into the technical details of the Domino model. So the Domino model is a neural operator. Neural operator meaning that it's infinitely scalable because it does point-wise evaluations, and I'll tell you what that means. But the model itself has three components. The first component is a geometry encoder. So the input to the Domino model is basically the STL of the geometry. So in this case, I'm showing an STL of an F1 car. The STL is processed through a geometry neural network, which is trained, which is trainable in the whole training process to basically embed the geometry, project the geometry onto a structured grid latent space. Once we have this geometry encoding, we basically sample a point in the domain. So this sample point is where you want to calculate or evaluate your fields. So if it's a volume field, you would sample this point in the volume. If it's a surface field that you want to evaluate, you'll sample it on the surface. Once the point is sampled, this is the second component of the domino model where we extract local geometric features. So we construct a subdomain around the sample point shown in blue here. And then we use the physical dimensions of the subdomain as well as the global geometry representation to calculate a local geometry encoding. And this happens using a point convolution and ball query, warp accelerated ball query operations. So once the local geometry encoding is available, then we aggregate the local geometry encoding with the point, the features of the point we want to calculate the solution on. But before we do that, we sample a stencil around, so sample a neighborhood and build a computational stencil around the point, calculate a basis functions using a neural network, and then basically aggregate the local geometry encoding and the basis functions to compute the solution on that point. And in the training phase, this solution is trained against ground truth data. And this solution can also be used to calculate physics-based losses. And at inference, all you need is the STL and a bunch of points sampled in your domain to calculate a solution. So all in all, this architecture, it's meshless. So at inference, you don't need meshes. It can model both surface and volume fields. So you can calculate flow fields anywhere in the volume as well as on the surface. Third, it has a basis in numerical methods, such as we build this computational stencil and then calculate nonlinear basis functions before we use them to compute the final solution. And finally, the most important thing is this ability to capture local geometry encoding, because global geometry encoding is a high-dimensional, heavy representation, and then conditioning that to your point may not be efficient. So we calculate enough information in the locality of this point that is useful to get an accurate prediction. Yeah, so this is basically the domino model. So next, I'll hand it over to Peter, who will describe some of the training mechanics and results that the Luminary team got while training this. Thank you.
Thank you so much, Rishi. So we took this framework and then we applied to the air SUV problem that you saw earlier. And as we generating more and more data set, we're continue doing the training and refining the model as we go forward. And it's great to see actually the training is quite efficient. So for the 1,000 data set to training on the surface, it took about 13 or so hours on one node of GPUs, and you can see the training loss has stabilized toward the end. And we're able to get a trained model and out of it, based kind of summarizing all the feeding all the data set that we have. Now, the first question you're probably going to ask is how accurate is the results is. That's also my very first question when our team put this together and looking at the results. Here I want to show you a couple points that in this design space, some of them are very accurate, some of them are not as accurate, and let's take a closer look. The first point, we again, this kind of randomly selected a few geometries and the design points. And this particular one, it's actually quite accurate. So if you look at the left-hand side is the CFD results, and the right-hand side is the inference predicted results from domino model. Drag is pretty much spot on. So we see that the same drag force. Downforce is about 6% off compared to the two models that we have. The surface results, it's pretty much, you can't really tell on the surface, but the quantity of interest here is about 6% off. Now let's pick another design. This is one of the design that didn't do too well. This particular one is at state 12. We basically name off our geometries. And the physics or CFD solve, the drag is about 74 Newton, and then the predicted one is about 70. So it's about 5% error on drag and about 10% on downforce. Now, to be honest, I'm actually really pleasantly surprised even to look at these results. So we're just starting with this initial data set we generated, and we're going to generate a whole lot more data. And I fully believe as we go forward, this accuracy is going to continue to improve. And if you're getting to 2%, 1% range, I think we can all agree that's going to be a very usable tool can be able to leverage in the design process. Now, if we take a step back, looking at the overall error across the entire data set, and in this plot on the right, the x-axis is the drag solved by CFD, and the y-axis is the drag predicted by the model. Now, if in the perfect world, if it's spot on, then it's all going to be clustering around the line over there, and right on the line, right? But you can see it's actually quite close. So it's well clustered around this, slope equal to 1 line there. The blue dots are the one that we use for the training, and the orange dots are the one that we deliberately not feed into the model, but use it as a validation so that we can test how the model performs on the design they have never seen before. So even with this very high drag point, the orange on the very top, and you can see actually pretty well. And these orange are the ones that the model have never seen. It's completely new design to the model. So across this entire data set so far, we're seeing about an average error about 2%. 94% of the prediction has 5% or less error. All prediction is within 10%. Now, it's may or may not be usable yet, but as the data size increase, we truly believe this is trending in the right direction, and we will have a tool that's going to be amazing for the industry to leverage for inferencing in the early design phase. Now, the last step, once the model is trained, validated, the last step is inferencing. And the nice part with a trained model, it's very lightweight, meaning the file size is fairly small compared to the data set itself. And it can be very portable as well. It can be deployed anywhere, offline, in the cloud, and it can be deployed in conjunction with the tool the designer actually used. We showed you earlier this video early in the presentation, but in this particular example, the inferencing model is deployed as a plugin to Blender. So as we talked about earlier, it's an amazing way that you can just inside a Blender, leverage the data set, leverage the inference model, predict what the drag is, and then as you add more design to it and making changes to the design, the tool is right there, giving you instant feedback. The nice part is that inferencing extremely fast, in the order of seconds, and it gives near real-time feedback to the designer on the performance. Now, if the speed is there and hopefully the accuracy continue to improve, we truly believe this is going to be a wonderful tool for the design engineers and studio engineer to be able to leverage in that early design phase. Now, I'm a huge fan of Vision Pro, and one of the things that I love to do is look at how we can actually incorporate spatial computing into the workflow. And one of the things we're working on, also collaborating with NVIDIA team, is to deploy an inferencing model into Vision Pro so that you can stream from Omniverse into Vision Pro to do inferencing and looking at the results. And I think that'll be a great future that we have a model that we can look at and morph and sculpt and inferencing real time inside Vision Pro. So hopefully today we show you a very exciting starting point, and we are at inflection point of a new way of doing aerodynamic design. And we're making this model available, and so that we can provide this data set to the community. And we show you a way to able to develop and chain the entire workflow together end to end, going from the geometry all the way to the framework of doing inferencing. We would love to excited to announce also that we are open source both the data set and the foundation model that's trained with Domino in this presentation. The 2000 DES simulation data set is already available today, and by the end of the year, we're going to get to 25,000 DDS simulation, which is an amazing large amount of data to be able to get to the accuracy that we need for those type of design. So if you're interested into accessing that, here's the website shift.luminarycloud.com, and you can request access. We also have made a sample dataset available for you to download right away, so you can test it out. And that is available both the surface data as well as the time average volume solution that we made available. And lastly, so here's my contact info, and here's Rishi's contact info. And if you're interested in try out Luminary Cloud for your own CFD needs, here's our platform. We do offer free trial, so you can sign up on our website and give a try. We also have presented at Auto CFD 4 workshop September last year. So if you're interested in looking at a VNV study that we've done, you can go to this website to download a white paper that we did for the VNV. Now, before we conclude, we love to do a quick poll. So I think it's good to see that we have a mix of both studio engineers as well as CFD practitioner that joining us. So on the screen, you'll see a poll that quickly pull up. So feel free to fill it out. And with that, we will move into the Q&A session. So if you have any questions for myself and for Rishi, and Rishi, you can jump on the camera as well. Feel free to type into the question window, and we'll address that live as we go forward. All right. So maybe, Rishi, I'll take the first one. So Deepak asked, which CAD software was used to generate shape and geometry designs? So if you saw the diagram earlier, we're agnostic to what tool in the end it's used. So you can use any CAD software to script it and to systematically generate design. For this particular work, we're actually using ANSA to morph the baseline geometry and generate the surface and volume mesh.
Oh, sorry, I could take the second and
yeah, go ahead.
I guess. Yeah. So the second question is there a confidence uncertainty measure for blind inference? So at the moment, we don't have an uncertainty quantification on the predicted result. But given the, but we could provide a confidence metric on the geometry that is being inferred, because we calculate a geometry encoding in the domino model. The embedding of the encoding can be compared with the embedding of the new geometry you're trying to solve, can be compared with the embeddings in the data set, and then you can come up with a confidence metric based on some distance score. Oh.
Taking the next one for you as well.
Yeah, I'll break it down. During training, you're randomly sampling query points from the geometry. That's right. Was the model able to generalize to query points which it has not seen during training? The answer to that is yes. We've tested that. So no matter how we sample those points, the model gives the same result. So there is very low sensitivity to the sampling algorithm used. And what's the order of the points we are sampling during training? So it really depends on the STL or the size of the STL. The framework, PhysicsNeMo framework, and the domino model, it has data pipes which are able to handle STLs in the order of millions. But if you generally STLs can be lighter, and those also work.
Yeah, and that next one asks about the results. So the CFD results generated by Luminary in the data set is both volume and surface. The inference is also, you can inference both the surface results, surface pressure and things like that, as well as the volume solution as well. And then I think the key nice thing about Domino is that you do not need a mesh to do inferencing. So all we feeding is just STL, and then that you can do inferencing on top of that. Cool. And then the next question is about transient simulation. So yeah, so we're talking about REN simulation generally on Luminary Cloud is about, I'd say 5 to 10 minutes range. Transient depends on what type of transient. So if we're talking about DES, it's on the order of an hour or so. And the nice thing is that Luminary, we developed our solver 5 years ago from scratch. It's a tailor-made solver that's GPU native and cloud native. So the combination of those, as well as the way we architect our solver, that empowers how fast we're able to run those simulations. And we're not on the methodology side, we're a finite volume second order solver. So solving to the level of accuracy you'd expect. The innovation is really how we implement a solver, deploy that on GPU resource and deploy on the cloud. And a second question, Rishi, maybe you can answer.
Yeah, I can take that. So the network has the ability to use mass momentum energy as constraints, but the model we've trained, model that has been trained for this work does not use that. But in the future, we will provide that capability to add these constraints to the training. Then you mentioned aggregating local basis functions into global network. Does that mean you need training data set defined for min-max bounds of the design space? Generally, this depends a lot on the use case, but for the external aerodynamics use case, the computational domain is quite bounded. So the volume that you're trying to model. Now in terms of now, let's say if you were to scale the domain 1,000 times smaller or 1,000 times bigger, although the solutions might not change if you keep the Reynolds number the same, but the ML model might struggle in doing that. But we take care of that by normalizing the coordinates. So as much as possible, we do normalizations and standardizations to the data, but there may be scenarios where you could break the model. The two examples for inference you showed, are they both part of the validation set? That's right. Yeah.
Yes, yeah. So we're picking some of the data set to show the difference or the higher accuracy and the low accuracy within that data set. And the last part you asked about the inferencing in Blender. So the plugin we developed, you can use any way of morphing geometry in Blender. So you can use a sculpting tool in Blender, or you can define a deformation cage to stretch the geometry in Blender. So we want to leave the freedom to the studio engineers. However, they typically use Blender to sculpt and change the geometry. The plugin, all it does is once the geometry is changed, and then it's a single click button to inference and get the CFD results on top, or inference results on top.
The next question is, we can use the pre-trained model and fine-tune it, say, bike geometry without catastrophic forgetting. So, of course, you could. I mean, this is an unanswered, unexplored territory. We would love to try something like this and then get back to you. The whole concept of fine-tuning and the methods used for fine-tuning, there is a lot of research going on that front as well. So it really depends on the method you're using for fine-tuning. If it's a predictor-corrector based method where you keep your original predictions and learn a correction on top of it, you still get your original predictions, right? So you can still keep your original model and then fine-tune the next model only for the specific bike use case. So you get the best of both worlds in that case. But it really depends on how you want to model that problem.
Maybe I can answer the next three questions altogether. Yeah. Actually. So, we started with about 1,000 data set that we trained. We're now up to 2,000 DDS simulations. This is also a learning experience for us and for the whole industry as well, to really know how big the data set need to be to get to the level of accuracy we expect, right? So that's why we're going to 25,000 DDS simulation data set to get to the level of accuracy we think we need. But it may be 10,000, it may be 5,000. So that's part of the journey we're embarking on to learn and to kind of validate what is necessary to get to the level of accuracy. But the part that is we truly believe is data is the critical component here, right? So I think the model is there, the infrastructure is there, the pipeline is there. The missing piece today is just how much data we can feed into it. That is high quality, high fidelity. It's also depend on the design space and problem set that we talk about. where we are today, we believe we want to train a tailored model for a subset of the CFD problem, right? So not a general purpose CFD solver that can do everything. Rather, the data set is going to be fairly focused, as well as the model is going to be fairly focused, in this case, SUV aerodynamic design. At Luminary, we're actually adding additional data set that we train and we are releasing as open source and can extend to other domains. So aerospace, we already done some work there. Turbo machinery, as one of the attendees comment on. So our goal is to release subsets of foundational model that is tailored for each specific industry and domain, as well as the pre-trained model for the type problem you are solving. And then, as we releasing it, then we can look at accuracy and then continue adding data to get to the level of accuracy you expect for each domain, for each industry. All right, and then there was a question on ground truth. So the ground truth in this case is using the CFD solution as the ground truth instead of test experiment data. But there is methodology, I think, Rishi, if you want to comment as well, is that incorporate also experiment data into this as well, but that's sort of a later stage.
Yeah, that's right. There is a possibility of building these multi-fidelity models. Yeah. The next one is there a particular reason for the neural operator was used as opposed to deeper nets? So deeper nets is it's basically new. So if you look at the architecture that we've used it, and if you were to map it to deeper nets, you would see similar structures in the sense that we have a branch net which does the geometry encoding, and then a trunk net which predicts on those sample points. You could, and that is typically how neural operators are structured, or at least deeper net is structured. So it has basis in deeper net, I would say, but we have made modifications over that to build this architecture.
So Sandeep asked a question about the accuracy of input physics simulation compared to experimental data. The reason we also choose the quarter scale aero SUV is that it has experimental data, slightly limited, but there are some public domain experiment data available. So that's actually the starting point before we even do that. We've done V&V to make sure that the initial data set is accurate enough, right? And obviously we don't have data set to compare once the geometry is morphed, but and we also done extensive V&V on our solver with the Auto CFD4 workshop, and I encourage you to take a look at the paper that we released there to make sure the physics simulation is as accurate as it can be before we start generating additional data sets. And the next question is how the rotating tire handle in this simulation. So Luminary Cloud Solver can do both rotating geometry as actually rotating in transient, or using a wall boundary condition like MRF to simulate that. So in this particular case here, we're using a boundary condition to simulate the effect of tire rotating, as well as the ground, right? The belt that's moving using boundary conditions. And the next one.
Yeah, the next one is about propagation of information and GNNs. I'm happy. So we did not use GNNs in this architecture. I'm happy to answer that question in another discussion, just in the interest of time. Yeah, but so feel free to reach out.
Yeah. So Jen, you asked about the Blender plugin. It's actually available under beta. So if anyone interested in the Blender plugin, you have my contact information. Feel free to reach out to us. We'd love to work with you to give you a test.
The next one is how about its accuracy compared to other architectures like AeroGraphNet? So very soon, in the next month or so, we are going to release a benchmarking paper where we have benchmarked the different architectures we have in PhysicsNeMo for the open source datasets, DriveRML and DriveNet. And we will also release the benchmarking utility. So a repo which will enable external users to bring their models and then benchmark them against any other models. And the speciality of this benchmarking utility is that it is going to encapsulate all the CAE specific, CFD specific benchmarks from capturing design trends, volume, surface, line plots, and so on. So, do you incorporate physical parameters or boundary conditions as well? Yes, we have the ability to do that. So if you have boundary conditions that are varying in your dataset and you want to model those, we have the ability to encode those into the network. Have you tried mesh graph nets versus Domino? We have, and we will be releasing a benchmarking paper, like I mentioned before.
And Clement asked about the mesh refinement influence on the results. So in this particular case, so Luminary has automatic mesh refinement methods. So it will automatically refine the mesh as it see fit. But for this particular data set, it's a fixed mesh. So we have not looked further into the effect of mesh refinement on the results. Cool. Well, thank you all for a lot of amazing questions, and really good to see a lot of interest in this space. I'll end this webinar with a quick video to show, kind of summarize what we talked about today. But I want to thank you all for attending the webinar today. I really think this is just the beginning point, right? We're seeing really promising results with this initial data set and with the methodology we developed together. And we're excited to see what can take further and to see how that may change our day-to-day as CFD practitioner and potentially the impact to external aerodynamic design in automotive. And thank you all for attending. And if any question you have for us further, please reach out to us. And I will wrap up here.